Hey, welcome guys. We're going to be going over today how to do inference for a slope. Now we've learned how to do calculations with linear regression lines and do a little bit of all the number crunching and interpretations that go along with that. But now we're going to do some inference. In other words, we're going to say, hey, can we estimate the true population slope, or can we run a test against the slope? So this first video is going to talk about the interval estimates. The video you see following this will be about tests. Let's begin with a little activity. You're going to want to go to staplet.com and follow along with these steps. On staplet.com, if you go down to activities and click on Old Faithful, this is a scatter plot of 263 eruptions in a month for the Old Faithful geyser in Yellowstone National Park. Here is a population slope, population regression line. Predicted wait time 33.3 plus 13.3 times the duration of how long it's erupting. The predicted wait time is how long between eruptions. So here's your scatter plot. And what we're going to do is we're going to take just one random sample of 15 here. And no surprise, you're going to get a different sample slope because it's only taken 15 of the numbers. And if you look at that number there, it's pretty close to my population slope. But or actually my population slope is 13.3. So it's a little bit off. But let's say we do a few more here. And oh, kind of all over the place. You would expect that to happen, but maybe I do 1,000. What happens? Starting to look familiar. Maybe I do another 1,000. And eventually, the more you do that, you're going to get something that's going to look like a normal curve. So the sampling distribution of the slope for uh, any sort of regression you're using is always going to kind of follow this mean and standard deviation, where the mean is going to be pretty close. In fact, exactly if you take every possible sample, uh, the same slope as the population slope. So 13.3 here, population slope, and 13.3 here. The standard deviation has a kind of a quirky calculation here. No need to memorize it because it's going to be on your formula sheet. So I'll show that to you on the next page. But that's how you do that. And let's get into how to do the calculations for it and talk about where those formulas are. Before we do that, let's just talk about notation. So you should be familiar with the B. That's going to be the slope. Now, in the past, we just called it our slope. This is actually our sample. Now, what we do is we use that to predict a population. So you'll see over here in this little fancy equation with all the Greek letters, you'll see uppercase beta, and that's going to be your population slope. That's what we're trying to predict. It's really unreasonable to take regression analysis for hundreds of points, maybe thousands of points. So we do a sample and then we try to estimate from there. So that's what we're really going to be doing. You can do the same thing with intercepts if you want to. They don't have as much meaning to it, but you'll notice a slight difference here with this sample y-intercept versus this population y-intercept. But it's very unlikely you're going to have anything to work with for that. And if you do, you'll get some steps along the way. There's also the y hat. The notation for the population regression line, instead of y hat, we just do like the mu of y. So it's basically the mean of all the y values for any given value of x. But again, our focus really is on slope because slope has the most meaning in the context of these problems. So you're going to see two formulas. These formulas are on your formula sheet. So the top of the formula for the standard deviation of the sampling distribution for the sample slope is simply the standard deviation of the residuals, but it's the population one. So you'll just see it as sigma. And then the denominator is going to have two things. Square root of n is, hopefully you're familiar with n, the sample size, and then the square root, the sigma x is going to be the standard deviation of the x values. So it's not really an intuitive thing, but that formula is provided to you, so we'll make it work in our calculations. So let's look at an example. Um, for the population of 263 Old Faithful eruptions for a particular month, the population regression line is mu y equals 33.3 plus 13.3x. The standard deviation of the residuals is sigma equals 6.47 minutes, and the standard deviation of the eruption duration, sigma x, is 1.18. Imagine taking a sample of 15 eruptions that occurred during this month and using the sample data to calculate B, the slope of the sample regression line, and Y, the wait time. So let's calculate the mean and interpret the mean of the sampling distribution. Nice thing about that one is it's just going to be, you just use that mu symbol, um, lowercase b, and that literally is the population slope. In that case here, we are provided it. So 13.3. So that's the calculation part. Not really that hard. Let's actually look at the standard deviation while we're at it. So verify the 10% condition is met. You have to use that 10% condition to calculate the spread. So since we're doing a sample of size 15, we just have to check, is 15 less than 10% of the population? And our population here is 263 points. That's going to be your capital N. Well, that's going to be true. Okay, 15 is less than 10% of 263. So we're safe to use the standard deviation formula. And again, that formula is sigma b is the sigma, which is the standard deviation of the residuals, the population one, divided by sigma x. Oh man, there's so many sigmas, times the square root of n. So let's plug everything that we have in sigma. That top number is going to be 6.47. This number here is going to be 1.18. And of course, n is going to be your sample size. That's going to be 15. So if you throw all that into the calculator, you're going to get, oh, let's say 6.47 divided by 1.18 times the square root of 15. I don't know what that is in my head, so throw that into a calculator and you will get, hold on, let me get my calculator out. Looks like 1.415, which if you remember the website, that's very, 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 very close to that number that was calculated on there. So let's talk about our interpretations. So we've calculated the mean and standard deviation. We verified the 10% condition to be able to use the standard deviation formula. As far as the interpretations go, for mean, it's pretty simple. For all random samples of whatever your size is, so 15 eruptions from this month. So every possible random sample, if you average those slopes, you're going to get the population slope. So for all random samples of 15 eruptions from this month, the average of all the slopes is going to be about 13.3. Standard deviation is the typical distance from the mean. So you would say something like this. For all random samples of 15 eruptions from this month, the sample slopes typically vary by about 1.416 from the population slope. So it's the typical distance from the population slope, all these little sample slopes. So that's the write-up for those. We want to make sure that we are, let me squeeze this in here, make it a little narrower. There we go. We want to make sure that we're writing this up correctly in context of the problem too. So we always talk about what we're dealing with. So here's one that you can try. Pause the video. After you read the question, you can pause the video. Here's the scatter plot showing the relationship between X, average driving distance in yards, and Y is the average score for 164 LPGA players in 2021. Lower scores in golf are better, so you'll see a negative association, hopefully. The population regression line is provided right here. Let's circle that. So 81.9886 minus 0.0392. The standard deviation is of the residuals is 1.29. That's going to be your sigma, just the sigma. And your standard deviation of the x values for the driving distance is 10.17 yards. So imagine we take a random sample of 12 players. 12, we can handle 12. That's not too many to put in. Calculate the slope. We get a scoring average. We make some predictions. Let's go ahead and calculate, interpret the mean of the sampling distribution and verify the 10% condition is met and calculate, interpret the standard deviation of the sampling distribution. So you should probably pause this because I'm going to put the answer on the board and I don't want you just copying it down. So pause the video and unpause it and you'll see how I answer it. All right, there are my calculations. The slope was already in the formula, so we didn't have to do any work for that. Negative 0.0392. The 12 sample size is less than 10% of 164, so we can go ahead and use our formula. We'll plug in the numbers that are in there, and you get about 0.0366. And your write-up should be something like this. For all random samples of 12 LPGA players from 2021, the average of all the slopes is going to be about negative 0.0392. And for the standard deviation, you would say something like, for all random samples of 12 LPGA players from 2021, the sample slopes will typically vary by about 0.0366 from the population slope. And that's just about as much as we'll do with sampling distributions, because everything else is going to be more practical. And try to calculate intervals or run a test in the next video. So let's look at the next example. Well, we can't do an example before we check conditions. And as far as conditions are go, you're going to see some of these that are familiar. Um, Random, yeah, we can't sample more than 10% of a population. So make sure you check your 10% condition if you're sampling without replacement. Now, if you're doing random assignment, if you're doing random assignment in an experiment, we don't check that condition, okay? This is only if you're pulling from a random sample and you're trying to make inference to a larger group, okay? But you got to check the random condition regardless. You also have to meet that normal condition. Actually, I want to call it the approximately normal because it's not really normal, but we want to make sure our sampling distribution is approximately normal. How do you do that? Well, a couple reasons, a couple things. You want to have a sample size that's 30 or more. That's your central limit theorem, but you're not going to really see that very much because are you really going to put in 30 points of data? Nah. So you plot your data like you would. Now you're going to get residuals. Really, it's all about the y values, your y values. So your residuals are your kind of driver here. You can plot your residuals on a dot plot, or you can make a histogram or a box plot, whatever it is. But you plot your residuals and you say, do my residuals have any sort of skewness or outliers? And if you see that being the case here, like this is bad, we don't want to use that. Or if you had like, maybe a histogram that looked like this, and then you had super skewed data, like really skewed, and maybe even an outlier over here, that would not be good. But if you have a little bit of variation, but no super strong skewness or outliers, that meets the approximately normal condition. Again, you should be familiar with those. What you're probably not familiar with are these conditions. So there's a couple new ones here. Because it's a linear thing, we got to make sure that we check a couple additional ones. Here they are. First, and this is going to sound real dumb, but this is just the linear condition. Is it linear? Like you can't really do it if it's not linear, right? So what does it mean to be linear? Well, you check your residual plot. Do you see any sort of curve pattern to it? That's bad. If there was a random scatter, from your residual plot, that'd be pretty good, right? No, nothing that would indicate it's not a linear regression. Or if you can just want to be lazy and look at your LSRL and just kind of tilt your head a little bit and look at that and say, oh yeah, I can see kind of a random scatter there. So that's a good thing. So yes, you have to meet that linear condition. A roughly linear pattern will present itself hopefully pretty obviously. But there's another condition that's called the equal SD. Oh, I went off the screen for a little bit. Equal standard deviation. What that is basically like if you were to basically run a little band across there, you want a relatively consistent width above and below throughout. You can see a little bit of variation there. What you don't want, that's okay. That's called equal variance or equal standard deviation. You can call it either one. It does not really matter. You can also look at it like if you see some sort of triangle cone type shape, where it's kind of moving out, whether it's going this way, oh, I can't, my camera's gone off there, or this way. If it's getting more spread out, the further away you go, that's a bad thing. Okay, so we want to make sure we have equal variance, roughly equal variance throughout. Now, how you going to remember all these, hopefully, is with a little acronym called linear, and that's LNER, linear. Linear, random scatter, approximately normal, no little strong skewness or outliers in your residuals. Equal variance, no triangular type shape, no coning out. And then the random condition must be checked, of course. So LNER in whatever order you prefer, but honestly, if you don't want to be tacky, I stick with random and I do normal and I put the L and the E in between in whatever order you want to put those in. So RLEN, LNER, linear, linear. We're going to eat some linear, lunch and dinner, so linear. All right, so now that we've done that, we can do some problems. Remember, here are your formulas for the sampling distribution for the mean and the standard deviation of the slope. All right, so now that we've gotten all the conditions out of the way, the interval itself, the calculation is not too bad. You're going to usually be provided with all the information you'll need to be able to plug stuff in, except for the critical value. So what that's going to look like is you're going to have this computer output usually, and you're going to see your slope, and you're going to see your standard error of the slope, that number right to the right of your slope. That's this thing right here. And the number for the slope is going to be there. That's your statistic. And your critical value, because this is quantitative data, is going to be a t star. And we get our t star from inverse t or our table B. The t star is going to have n minus 2 degrees of freedom because it is two variable data. So you just got to be mindful that you're subtracting 2 from your sample size, not 1. So let's look into calculating that from an example. Before we do that, when we set up our intervals, we want to make sure in a free response, we're capturing the correct things. So we want to make sure we're doing the name of the procedure, define the parameter, check your conditions, linear, do your calculations, in this case, calculate your interval, and then draw your conclusion. We are 95% confident that the interval from this to this captures the true slope of the population. So here's your formula again. Let's calculate with it. So the question says, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development, and researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ scores. A snap of a rubber band of the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later assured that the children's IQ at age 3 years using the Stanford-Binet IQ test. The table contains data from a random sample of 38 infants. Calculate a 95% confidence interval for the true population slope. Assume all conditions have been met. So we're just really going to go about the calculations for this one. We'll save our a whole write-up for later. First, we'll need the formula. So it's B plus or minus T star times standard error of the slope, SB. And we got two of those three things already in the table. There's your B, there's your standard error. So we're really just going to plug in 1.4929. And then for your standard error, you're going to do 0.4870. Now we don't know the T star. So, we're going to just kind of leave that as T star for a minute. And we'll figure out how to calculate that by using technology or table B. Show you both ways, but honestly, technology is going to be the best way to do it. So let's do a little refresher on how to get T star using technology. What you'll do is you'll pull out your calculator, you go to second vars, and you're going to inverse T. Now remember with that, you have to, I already have it in here, but you have to average your confidence level with 1. So you can do 1.95 or 1 plus 0.95 if you want to see that calculation. And then your degree of freedom will always be the number in the sample size minus 2. So you can put 36 or you can do 38 minus 2, whatever works for you. And you're going to get a T star of 2.028. And honestly, this is the most accurate number you're going to use. So why not just use that, right? So you get a 2.028. Let me write down the steps to get that. So you'll do inverse T. You're going to be your area is going to be I'll just do 1.95 divided by 2, and your degree of freedom is going to be 38 minus 2. So that T is going to be, I already figured what it was, 2.028. So we'll replace that over here and we'll rewrite our formula. So now that we have 2.028 for our T, T star, we can do our whole calculation. So it's going to be 1.4929 plus or minus 2.028 multiplied by 0.4870. Remember, guys, the number here at the after the plus or minus is your margin of error. So if you're asked what the margin of error is, just multiply those two numbers together. And then you can do your calculation from there. All right, so that's going to give you a 1 point. Let me do it over here. So 1.4929 minus 2.028 multiplied by 0.487. And then we'll go up and maybe not type the wrong decimals in. That would be helpful. That's more like it. And then we'll do the same thing with a plus. And you're getting an interval from 0.505 to 2.4805. So your final interval will be 0.585505 to 2.4805. So we'll go ahead and circle that. And if you were making an interpretation of this, you would say we are 95% confident that the interval between 0.505 and 2.4805 captures the true population slope for this set of data in context. Now, as far as the table goes, let me show you table B here, how you can get the T star, and it's going to be a little bit off because it's rounding. Now, if y'all looking at this table, which is provided to you in your online reference sheet, you look at your 95%. Now, because our sample size was 38, we actually technically following the rules here. We have to go down to 30 because we don't have a 36 in here. So if you meet those up, you're going to get a T star of 2.042, and which is a little bit off from this 2.028. So I would recommend this one here, just because it's more accurate. And why not be more accurate? Here's a follow-up question. Does the interval provide convincing evidence of a positive linear relationship? And if you look at the numbers here, they're all positive. So yeah, so you'll say something like yes. You gotta say yes or no. Since the entire interval for the slope estimate is greater than zero, there is convincing evidence of a positive linear relationship between these variables. So it's as simple as that sometimes. Other times it might be a little more complicated, like it might say, is there evidence of a linear relationship? In this case, you would just say, well, yes, since zero is not contained in the interval, we have evidence of some sort of linear relationship, but you don't have to get into the positive or negative aspect of it. Let's look at another example. Now, here's an example that we've done before. Once again, we have data comparing the price of Ford F-150 Super Crew to the miles driven for our random sample of 16 used Ford F-150 Super Crew trucks. And you see the miles driven and the price. And in this case here, because we have raw data, we can actually enter it into a calculator and let the calculator do the interval or test if we're doing a test. Now, that's a lot of numbers to type in, and you probably don't want to type those in, but I already have them typed in, so you can see how I do it, and just kind of watch the process if you don't want to do it yourself. So you're going to go through and you're going to enter in all 16 points of data, making sure you enter them in accurately. And to get the interval simply from this, you'll go to Stat, Tests, and you'll go to, I actually just press up a couple times, and there's two things. There's linreg t-test, linear regression t-test, and linreg t-interval, linear regression t-interval. So of course we're doing an interval. We want to click L1 and L2, keep frequency as 1. C level is whatever the confidence level is, so 90%. So we'll leave that as 0.9. And if you want to store this in Y1, you can just do alpha, trace, enter. Put on calculate, and it's going to give you all the information you need. It's going to give you the slope, the y-intercept, the standard deviation of the residuals for the sample, the degree of freedom, and even the r squared and the r. Now we're really just concerned about the interval, so negative 0.2174 to negative 0.1084. We'll write that down and then answer the question to follow. And of course, our follow-up question is just kind of a, hey, does the interval give us some evidence, in this case, of a negative linear relationship? And since all the values are below zero, you would say something like, yeah, the interval is entirely below zero. Therefore, we have convincing evidence of a negative linear relationship. There's a little bit more to it than that. So this is if you just had the data here, but let's say you already provided everything. You're already given an output. Well, the problem is that the computer's not going to give you outright an interval like the calculator will. It'll give you something more like this. So you'll likely have a combination of all this stuff here. You'll have like a graph of the residuals that's going to be used for your normal condition. You'll have a residual plot, and that's going to help you with your equal variance or equal standard deviation. And it's going to help you with your linear condition when you're checking that. And you can also just get a scatter plot so you can see what the data looks like. But the numbers are going to be in here. And remember, the only numbers that we really care for an interval are going to be your slope and your standard error of the slope, SEB, SB. So those two are your kind of like numbers there. The conditions will be over here. We're going to go ahead and construct a 90% confidence interval using this, and we're going to write it up the correct way. So just to get the name out of the way, we want to name what we're doing first. We'll say it's a linear regression T interval for B. You can say lin reg T interval if you want. But you got to define what the population slope is. So in this case, it's the slope of the population regression line for price versus miles for the Ford F-150s. So as far as the conditions go, that's going to take you the most amount of space. So remember, we're checking our the acronym is LNER, linear. I do like to do the random and normal kind of bookended with the linear and equal variance. So we just want to make sure we check that and write something like that. So let's look at the graph here. You can see that the randomness just comes from, hey, it was 16 random selected Ford F-150s. You can see also that the band of residuals is roughly the same, so there's equal variance and a random scatter. So I kind of take care of those together. And as far as the residuals go for the normal condition, you look at the you're going to get a graph of like the residual themselves, not the residual plot, but just a one variable. Hey, here are the residuals. Do you see any strong skewness or outliers? And that's your approximately normal condition. We have to do that because we only have 16 points. We don't have 30 points, so we can't use the central limit theorem. Um, so let's write all that up. So we'll talk about it just in the order I prefer. I say random sample is 16 trucks. When you're doing random sampling, we want to sample less than 10% of your population. So yeah, there's going to be more than 160 of these trucks in the world. So our linear condition is also met. There's no curve in the scatter plot or random, and there's a random scatter of points. Our equal standard deviation condition is met, and our normal condition is met because the graph of the residuals shows no strong skewness or outliers. Notice I'm not getting too wordy with the context on there. We just don't have time for that in the free response. So, don't try to focus everything on conditions. Just kind of hit them up, and then we can do our calculations. All right, let's talk about calculations now. Calculations has the formula. Remember, it's just going to be B plus or minus T star times S standard error of the slope, so SB, SEB. So in this case here, of course, that's going to be from the actual computer readout. Let's take a look. And you see your slope, negative 0.16292, and your SEB 0.03096. So those are given to us. We're going to write them down and do our calculation and get that T star. So I've thrown in those slope and standard error into the formula. I don't have the T star yet. So remember, you're going to go into your inverse T for that. Highly recommend that over the table B, just easier to do. You do your 1.9 divided by 2. Remember to add that 90% to 1 and get the average. And then the degree of freedom will be the sample size minus 2, so 14. So we'll go to our inverse T. We'll calculate that. Second vars 4. And we'll do 1.9 or 1 plus 0.9 divided by 2. And for our degree of freedom, we'll do 14 or 16 minus 2. And you'll get a T star of 1.7613. And then we'll use that to make our final calculations. Now, there really is no reason to write the margin of error unless it specifically asks for it. So I would just kind of revert to typing everything in um, just very carefully here. I do the minus first since we want to do our small number. So 1.7613 parentheses 0.0306096. Close that up, and you're going to get the low end. Then you can just scroll up, press enter, and just edit that minus to a plus. Get your high end, and you'll get your interval between negative 0.217 and negative 0.108. And that's close enough. Negative 0.217 and negative 0.108. And finally, for your conclusion, you'll just say we are 90% confident that the interval from negative 0.217 to negative 0.108 captures the true slope for the truck price versus miles driven for these types of trucks. So that's your complete write-up. The calculations, hopefully they're not too bad. You do have to do some work. In this case here, if you're to get your T-star and calculate it, your calculator will only do the interval in its entirety if you have the raw data. So like when we had the truck data earlier and we put it in, it got us a similar set of data, but you're likely not going to have that. So do the check understanding next, and it'll just give you a computer readout, and then you can just double check the calculations and make sure you're on the right track. So let's look at the next problem, and that'll be our last one for this video. The question is, a physics class did an experiment in which they dropped 70 paper helicopters from various heights. Each helicopter was assigned at random to a drop height. The class suspects that helicopters dropped from a greater height will take longer to land on the ground. Here are a scatter plot, residual plot, and histogram of the residuals created from the LSRL relating y, flight time, and x, drop time, along with computer output of the regression model. Your question. Construct and interpret a 95% confidence interval for the slope of the true regression line. And then a follow-up. The class suspects that helicopters drop from a greater height will take longer to land on the ground. Does the confidence interval you created just give convincing evidence to justify this answer? So try that out. Pause the video. See what you can do. All right, here is part A. You can kind of read through that and see what you see. It's a linear regression T interval for beta. Beta is the slope of the population regression line of flight time versus drop height. So you want to name your procedure and parameter. You got to check your conditions. So always refer to those graphs here. In this case here, let me make those a little bit to the top. So you can see that it does say random assignment. The helicopters were randomly assigned various heights. And also, residual plot has a random scatter. So that would indicate it's a linear model is a good fit. There's a roughly equal variance, maybe a little bit off here, but in general, it's pretty solidly banded, better than not. And then the residuals themselves, when graphed, show no strong skewness or outliers, but that doesn't matter because we have a large sample size, so it's only 70. So we can actually say our central limit theorem is met here. Your calculations. This is really all the work you got to show. Now, you have to know how to get T-star. You don't necessarily have to show the steps to calculate it. So remember again, this is a 95% confidence interval, and there are 70. So you would do second vars inverse T, do 1.95 divided by 2, and put 68 in the degree of freedom. And you'll get 1.995 as your T-star. Then you can use that to make your calculation for your interval and do your final write-up. We are 95% confident that the interval from 0.0017 to 0.0098 captures the true slope of flight time versus drop height for paper helicopters like these. And then a follow-up question would just be something like, hey, the class suspects that when you drop something from a higher height, it's going to take longer to land on the ground. And that's like a duh. Of course that's going to happen. But um, the write-up for that would be kind of based off of your interval. So let's look at what that looks like here. Maybe don't write duh when you're typing it, but you can say yes, greater height and longer time in the air is a positive relationship. Since the entire interval for the slope is positive, there is convincing evidence that this is true. And that concludes the lesson on intervals. Hopefully it wasn't too bad for you. The next video we'll talk about how to do significance tests. Oops, where did I go? There I am. For the population slope. So stay tuned. Thanks for watching.